Let's kick off by comparing two major ways to access large language models: OpenAI's API and Hugging Face's Transformers library. OpenAI offers a fully managed serverless commercial endpoint, meaning you interact with their models via standard HTTP REST requests and pay strictly per token consumed. There's zero infrastructure setup required, making it ideal for rapid prototyping. Contrast, Hugging Face Transformers is an open-source framework that lets you load and run open-weight models locally or on private cloud instances. You gain total control over the model weights, but you must manage your own GPU infrastructure and software optimization stacks. For example, a startup might use OpenAI's API to quickly build a proof-of-concept app, then migrate to Hugging Face on AWS as they scale and face higher API costs. Streaming, often enabled with stream equals true and LLM APIs, changes how responses are delivered. Instead of waiting for the entire answer to be generated server-side, streaming returns text token by token as it's produced. This uses server-sent events SSE to stream chunks over an open HTTP connection, reducing the time to first token TTFT for users. In a web-based chat interface, streaming means users see text appear instantly, word by word, rather than staring at a loading spinner for several seconds while a long answer compiles. This approach greatly improves user experience, especially for lengthy responses. Handling API rate limits is crucial for robust applications. When an API throws an HTTP 429 too many requests error, your application should catch the exception and pause for a base delay time. With each consecutive failure, this delay doubles and a small random variable, known as jitter, is added. This prevents multiple distributed system workers from retrying at the exact same millisecond, smoothing out traffic and avoiding further blocks. For example, a background worker processing thousands of receipts waits 1.2 seconds, then 2.5 seconds, then 4.8 seconds, until the API limits clear. This approach ensures reliability and prevents service interruptions. Understanding the cost of running an LLM API in production is essential. The primary factors include input token volume, prompt and context data, output token volume, generated text, model tier selection, advanced versus lightweight models, and total request volume over time. For instance, running an automated customer service agent that ingests large documentation per conversation can quickly rack up API bills, especially if premium models are used for every query. Prompt optimization and model routing become vital to control costs and ensure efficient resource use. Software developers can minimize LLM API token costs by implementing a semantic cache layer such as GPTCache or Redis to store past question and answer pairs, aggressively pruning or summarizing old chat histories, and using model routing to send simple tasks to cheaper models while reserving complex reasoning for premium models are effective strategies. For example, if a user requests "summarize my account history" twice, the system fetches the summary from a Redis cache the second time, reducing API costs and response times to 0 for that request. Difference between max tokens and completion tokens in an API payload is important for controlling output. Max tokens is a user-defined hard limit set in the request payload, instructing the model to stop generating text once it hits that threshold. Is a metric returned in the API usage metadata, telling you exactly how many tokens the model generated before finishing. For example, setting max tokens to 50 ensures only a short summary snippet is produced, and if the model tries to write a longer explanation, it will cut off mid-sentence at the 50th token, returning a finish reason of length. Embedding API and a chat completion API serve different purposes. Chat completion APIs take text and generate new text sequentially, ideal for conversational interfaces. Embedding APIs, on the other hand, convert a block of text into a fixed-length vector array of floating-point numbers representing its semantic meaning in vector space. In a Retrieval-Augmented Generation (RAG) system, you pass a user's question through an embedding API to get a vector, then use this vector to search a database for matching documentation snippets to inject into the prompt. This enables advanced search and context retrieval capabilities. Processing thousands of API requests concurrently is made possible with asynchronous programming in Python. By using Python's Asyncio library and an asynchronous API client like OpenAI, you can fire off multiple network requests without blocking the main execution thread. For example, a script classifying the sentiment of 5,000 product reviews would take hours with asynchronous for loop, as each request waits for the previous one to finish. Using Asyncio gather, the script fires hundreds of requests at once, completing the batch in minutes. This approach is essential for scalable data processing. Finish reason field in an API response payload is a metadata string explaining why the generation process stopped. Common values include stop, natural completion or stop sequence, length, hit the max tokens limit, or content filter blocked by safety guardrails. For example, in an automated code generation app, if your parser encounters a truncated or broken block of JSON, you check the API response metadata. If finish reason is length, your application can automatically fire a follow-up request to continue generating where it left off, ensuring seamless output. Stop sequences are arrays of custom strings passed to the API. When the model generates a token matching one of these strings, it stops text generation immediately. This is useful for optimizing response control and saving on unnecessary token generation. For example, when building a web scraper that extracts data into a bulleted list, you can configure a stop sequence of \n. As soon as the model finishes generating the first complete line and hits a newline character, it stops, preventing extra, unwanted text and reducing costs. Seed parameter and system fingerprint in hosted LLM APIs serve distinct purposes. The seed parameter forces the backend cluster to use a deterministic path, making outputs reproducible. The system fingerprint is a hash string returned by the server, indicating the current backend hardware and software configuration running your request. For example, during automated unit testing of a prompt pipeline, you set seed equals 42. If your tests suddenly start failing, you check the system fingerprint. If the hash has changed, it tells you the model provider updated their backend infrastructure, causing slight changes in output behavior. Function calling, or tool use via API, involves passing an array of tool descriptions formatted as JSON schemas alongside the prompt. The model analyzes the request and, instead of replying with conversational text, outputs a structured JSON object containing the name of a function and the specific arguments needed to execute it. For example, a user tells a virtual assistant app, "Check the weather in Paris." The model returns a structured payload which your backend code reads, queries a real-world weather database, and sends the result back to the LLM to build a final response. Inference latency in LLM APIs is measured by time to first token (TTFT) and time per output token (TPOT). TTFT is the time elapsed between sending a request and receiving the very first token, reflecting prompt processing and system initialization delay. TPOT is the average time it takes to generate each consecutive token, tracking the physical generation speed of the model. In a customer service chat app, a low TTFT is critical to ensure users see an immediate response, preventing them from assuming the app is frozen, even if a long total response takes a few seconds to finish printing out. Passing environment API keys directly within client-side code poses significant security risks. Client-side code, such as React applications or mobile apps, can be easily inspected by end users. Exposing an API key there allows anyone to copy it and use it for their own projects, leading to massive financial charges or service suspensions. For example, a developer hardcodes an OpenAI secret API key inside a front-end React component. A malicious user can extract the key from the browser's developer console and run heavy LLM workloads, exhausting the developer's account balance in hours. Hugging face pipelines simplify the process of running models by abstracting away tokenization, model forward pass, and output post-processing steps into a single high-level function call. For example, calling pipeline sentiment analysis automatically handles taking a raw string like "I love this product," turning it into token IDs, passing those IDs through the neural network to get logit scores, and mapping those scores back into a clean output dictionary. This makes it easy for developers to integrate complex models without worrying about low-level details. Save and reuse an open-weight model locally using Hugging Face. You download the model files with the from pretrained method and then use save pretrained /path/ to /folder to store the model weights and tokenizer configurations directly on your local disk. This is especially useful in secure, air-gapped enterprise server rooms with no external internet connection. You can initialize models by pointing the Hugging Face loading script directly to a local hard drive path, ensuring full control and offline operation. Quantized inference compresses a model's weight values by reducing their mathematical precision. Moving from 32-bit floating point numbers, FP32, to 16-bit FP16, 8-bit INT8, or 4-bit INT4 integers dramatically reduces the GPU VRAM required to run the model, with minimal impact on accuracy. For example, a raw unquantized open model might require 32 GB of GPU memory. By applying 4-bit quantization INT4, the model's footprint shrinks to around 6 GB, allowing it to run locally on a standard laptop or a cheap cloud instance. Logic bias parameter in LLM APIs allows you to manually increase or decrease the likelihood of specific tokens appearing in the model's output by modifying their raw logic values before the softmax calculation step. For example, when building an automated multiple-choice quiz engine, you can guarantee the model only outputs the letters A, B, C, or D by setting their logic bias values to +100. This blocks the model from generating any other words or conversational text, ensuring precise control over output. Managing the system prompt cleanly through API message objects is critical for modern instruction-following models. These models accept structured message arrays split by explicit roles: system, user, and assistant. The API uses these roles to inject specific separation tokens, helping the model distinguish developer instructions from user data. For example, passing core instructions via role, system, content, you are a read-only view. Ensures the model prioritizes system-level boundaries over conflicting text passed in the user chat role. Trailing whitespace at the end of an API prompt can impact text generation by splitting tokens unexpectedly, depending on how the underlying tokenizer handles spaces. In many architectures, a word with an appended space maps to a completely different token ID than the word on its own, which can confuse the model's initial generation patterns. For example, prompting an automated code generator with a line ending in trailing spaces may cause the tokenizer to misinterpret indentation tokens, resulting in broken syntax or formatting errors at the start of its response. Choosing between OpenAI's API and Hugging Face's Transformers library depends on your project's needs. OpenAI's API is best for quick deployment and minimal infrastructure management, while Hugging Face gives you flexibility and control for custom solutions. As your app scales, you may start with OpenAI for speed, then transition to Hugging Face for cost savings and customization. Understanding these trade-offs helps you plan your GenAI integration strategy effectively. Token streaming and LLM APIs offer several benefits. By delivering text token by token, users experience faster feedback and improved interactivity. This is especially valuable in chat interfaces, where immediate responses keep users engaged. Streaming reduces perceived latency and makes applications feel more responsive, even when generating long answers. Developers can leverage streaming to enhance user satisfaction and optimize performance. Robust retry logic with exponential backoff and jitter is essential for handling API rate limits. By catching HTTP 429 errors and implementing delays that double with each retry plus adding randomness, you prevent overwhelming the API and avoid getting blocked. This approach ensures smooth operation in distributed systems and maintains service reliability, even under heavy load. It's a best practice for any production-grade API integration. Managing LLM API costs requires careful planning. Monitor input and output token volumes, select appropriate model tiers, and track total request volume. Use prompt optimization and model routing to send simple queries to cheaper models, reserving premium models for complex tasks. These strategies help keep API bills under control and ensure sustainable production deployment. Semantic caching, using tools like GPTCache or Redis, stores past question and answer pairs to minimize repeated API calls. By fetching cached summaries or responses for repeated queries, you reduce both API costs and response times. This is especially useful in dashboards or applications where users frequently request similar information. Semantic caching is a powerful optimization for high-traffic GenAI apps. Model routing directs simple tasks to cheaper models and reserves premium models for complex reasoning. This approach optimizes both cost and performance. By analyzing task complexity, you can automate routing decisions, ensuring that each request uses the most appropriate model. Model routing is a key strategy for scalable and cost-effective GenAI deployments. Setting max tokens in API requests gives you precise control over output length. This prevents runaway generations and ensures responses fit your application's requirements. Completion tokens, returned in API metadata, let you monitor actual output and adjust limits as needed. Using these parameters together helps maintain consistency and manage costs. Embeddings are essential for semantic search, document retrieval, and context injection. By converting text into vector arrays, you can match user queries to relevant documentation or knowledge snippets. Embedding APIs power advanced features like Retrieval-Augmented Generation (RAG), enabling smarter and more context-aware GenAI applications. Asynchronous API calls in Python unlock massive scalability. By leveraging Asyncio and Async clients, you can process thousands of requests concurrently, reducing total execution time from hours to minutes. This is crucial for batch data processing, sentiment analysis, and other high-volume tasks in GenAI workflows. Automating follow-up requests based on the finish reason field ensures seamless output generation. If a response is cut off due to max tokens, your application can detect this and automatically request continuation. This approach maintains output quality and prevents incomplete results, especially in code generation or document processing. Using stop sequences in API calls allows you to control where text generation ends. By specifying custom strings, you can tailor responses to fit your application's needs and avoid paying for unnecessary tokens. This is especially useful in structured data extraction, web scraping, and list generation tasks. Setting the seed parameter in API requests ensures deterministic outputs, making results reproducible for testing and debugging. The system fingerprint lets you track backend changes, helping diagnose unexpected output variations. Together, these features support robust development and reliable GenAI pipelines. Function calling via API enables structured tool use. By passing JSON schemas, models can output function names and arguments, allowing backend systems to execute real-world actions. This approach powers virtual assistants, automation workflows, and advanced integrations, bridging conversational AI with actionable results. Monitoring TTFT and TPOT helps optimize user experience in GenAI apps. Low TTFT ensures users see immediate feedback, while efficient TPOT maintains fast output generation. By tracking these metrics, developers can fine-tune model performance and deliver responsive applications. Never expose API keys in client-side code. Always store keys securely on the server and use backend endpoints to proxy requests. This prevents unauthorized access, protects your account, and ensures compliance with security standards. Following best practices is essential for safe GenAI integrations. Hugging Face pipelines abstract complex model operations into simple function calls. This makes it easy to integrate sentiment analysis, text classification, and other tasks without deep technical knowledge. Developers can focus on application logic, relying on pipelines for efficient model execution. Saving and reusing models locally enables offline operations, crucial for secure environments. By storing model weights and tokenizer configurations on disk, you can run GenAI workflows without internet access. This supports enterprise security and compliance requirements, making Hugging Face ideal for sensitive deployments. Quantization reduces model size and memory requirements, enabling efficient inference on consumer hardware. By lowering precision from FP32 to FP16, INT8, or INT4, you can run large models on laptops or affordable cloud instances. This democratizes access to Gen AI capabilities and supports scalable deployments. Logic bias lets you control model output probabilities, tailoring responses for specific use cases. By adjusting token likelihoods, you can enforce strict answer formats such as multiple-choice quizzes or structured data outputs. This feature enhances precision and reliability in Gen AI applications. Using structured message objects for system prompts ensures clear boundaries between developer instructions and user data. This helps models follow rules accurately and prevents confusion from conflicting inputs. Clean prompt management is vital for reliable and predictable Gen AI behavior. Trailing whitespace can alter tokenization, leading to unexpected model outputs. By understanding how tokenizers handle spaces, you can avoid formatting errors and ensure consistent results. Always check prompts for unnecessary whitespace to maintain output quality in code generation and text processing tasks. Integrating Gen AI APIs involves choosing the right endpoint, managing costs, optimizing prompts, and ensuring secure key handling. By following best practices and leveraging advanced features like streaming, caching, and model routing, you can build scalable, efficient, and secure Gen AI applications for any use case. Scaling Gen AI solutions requires balancing speed, cost, and control. Start with managed APIs for rapid prototyping, then transition to open-weight models for customization and savings. Use asynchronous processing, semantic caching, and quantization to handle large volumes and diverse workloads efficiently. Modern Gen AI APIs offer advanced features like function calling, logic bias, and structured prompts. Leveraging these capabilities enables powerful integrations, precise output control, and seamless automation. Stay updated with API documentation to unlock the full potential of your Gen AI projects. Master Gen AI API integration, understand the differences between managed and open-source endpoints, optimize for cost and performance, and follow security best practices. Use streaming, caching, and model routing to enhance user experience and efficiency. By applying these principles, you can build robust, scalable, and innovative Gen AI solutions that meet your business needs.